Uh, Good evening, everybody, and welcome to another meeting of the Parliamentary and Scientific Committee. You're all very, very welcome to this discussion on the UK National Quantum Programme. This has been organised in partnership with Innovate UK, and I'm sure we're in for a very interesting and informative meeting as always. However, before we get on to the substance of the meeting, I suppose, I would very much like to recognise the enormous contribution that the Duke of Edinburgh made to the Science and Engineering community, and particularly to this committee. Some of you will know, but some may not, that from the late 70s until 1986, the Duke of Edinburgh was actually our president. And was a big supporter of the work of the committee. Indeed, when we celebrated our 75th anniversary back in 2014, it was through his very kind offices that we managed to hold a reception actually in Buckingham Palace. And so he will be a great loss, not only to his family and all that knew him personally, but to the wider science and engineering community. So I would very much like to observe a minute's silence in honour of him. But while we do that, can I also draw to your attention the very sad news that Ian Gibson has also died. Ian was a Member of Parliament for Norwich North, and like myself and my immediate predecessor, he managed to chair both the Parliamentary and Scientific Committee and the Science and Technology Committee. And again, it will be a sad loss, and I'm sure we send our sincere condolences to his family and friends. So I think it would be fitting, therefore, to observe a minute's silence, after which we can continue with our meeting. Thank you very much indeed. Right, on to the substance of this evening. And as I said, this is a discussion about the UK National Quantum Programme, and to have, or to explore that and help us all understand the importance of this emerging and growing technology, we have three excellent speakers. We have Dr. Ilana Wisby, who is Chief Executive of the Oxford Quantum Circuits, I should say. Roger McKinley, Challenge Director, Quantum Technologies UKRI, and Professor Sir Peter Knight, Senior Research Investigator at Imperial College London, and a former President of the Institute of Physics. So welcome to all three of you. Each of you have approximately 10 minutes to talk to us and to give us our presentations, after which, and we will hear all three of you first, I will then be going to questions from our attendees. If I could encourage anyone who wishes to ask a question, please to use the Q&A function, which you should find at the bottom of your Zoom window, because that way we've got all the questions marshaled in one place, rather than trying to pick them up from the chat or from raising hands. So, as I say, please do use the Q&A. When I call you to ask your question, you'll be unmuted and able to ask it in person. I think that's probably all I need to say at this point, other than to remind everyone who is on the panel to keep muted when they're not making a contribution. purely and simply because it improves the sound quality and makes it easier for us all to hear what is being said. So therefore, without further ado, I'm going to pass over to our first speaker, which is Alana Wisby. Alana, we look forward to hearing what you have to say.
Thank you, and thank you for the kind introduction and invite to talk to you about quantum today. So we'll jump straight through because 10 minutes isn't much time to give a very high-level intro to all of quantum. Quantum, first of all, is, well, it's a complete paradigm shift in terms of the way that the world works. The quantum world at the scale of atoms and below is incredibly paradoxical and bizarre. Particles appear to simultaneously both be here and also not be here, or be mysteriously entangled at distances. So really, quantum technology is about harnessing all of these very strange and, in the classical world, not something we see on a day-to-day basis phenomena, to create brand new technologies which have absolutely extraordinary capabilities. And, I've got this candle to a light bulb moment here because we are absolutely talking about a true paradigm shift with capability. And as with any type of paradigm shift, technological or otherwise, it is almost impossible to truly predict the full extent of the ramifications of quantum technology. Now, quantum, I recognize here, I'm talking to probably people that are more into the philosophy side and a little bit about the history. So I wanted to just cover a little bit briefly about this. Quantum mechanics first emerged in actually around the 1900s. And basically what it does is it describes nature at its smallest scales, so at the nanoscale. And it predicts the world at this very, very fundamental level. So we're talking about atoms and photons. And it ultimately boils down to the fact that at the atomic and the photonic level, suddenly things become a bit weird, and actually everything is quite random and quite uncertain. And these ideas provoked, intense philosophical debates and controversy when they were first developed. And it is something which in many ways contradicts kind of our everyday experience. So you can imagine a world, for example, in which, if you're playing a game of billiards with a billiard ball, it rolls, we know how it rolls, we can describe that using standard mechanics. But if we start to move into the quantum world, that single billiard ball follows quantum laws rather than the rules of the everyday. And it might be that as you hit it, it's suddenly liable to disappear through the table at any moment. So it's pretty different in that way. And all of this, despite all of this kind of confusion or unpredictability, actually there's a ton of mathematics. It's called quantum mechanics, and the maths works incredibly well. So this was first developed in around the 1930s, and there's a huge amount of rigorous formulation that describe quantum mechanics and explain many of the phenomena that we would want to see. So we have now a new understanding described by quantum mechanics of lights, of properties of light and of properties of material. And that led to a huge amount of initial innovation. So we call this the first paradigm shift, effectively, or the first quantum revolution, which gave us things like lasers and transistors, which of course then led the way for computers and internet and smartphones and all of these things that have already drastically changed our lives. And that already was happening, from the 1930s. But then as we moved to the 1980s, scientists managed to develop methods for measuring and controlling individual atoms and photons. That means that they could then suddenly manipulate all of this theoretical maths and create applications where they can apply this maths to do things that we never ever could have dreamed of before. So trapping individual atoms, for example. And this gives way to even more exciting capabilities. It also first gave way to theory of, say, quantum computation. We know, for example, Feynman as kind of the father of that element of things as well. So there's a huge amount of maths, but we were only really able to start applying it into application, giving way to the second quantum revolution starting around the 1980s. So history aside, what actually is quantum? Well, what I'm going to do is run you through some very high level key principles to help describe what quantum is, and you will all leave here absolutely quantum experts by the end of this set time together now. So firstly, we have quantum, the word itself. What we know is that we're now talking about energy which is discrete. So we're talking about not just having a continuous spectrum, but having individual energy levels. So if you started to think about this, say you're in your kitchen and you've got your shelves and you've got a jar of jam and it's sat on one specific shelf. Suddenly, if you say you knocked that jar of jam, it could go and you give it a small kick and it will jump instantly from one level to the other. It's either on one shelf or another shelf. That is called a quantum leap in terms of the jam world. It also could describe, if you're thinking about driving your car and you move and you press the accelerator, instead of kind of going from 0 to 80, you're either sat at 5 miles an hour or you're sat at 80 miles per hour, and it's a discrete level. So that's quantum at its core in terms of discrete energy levels. We then move on to some of the more quantum toolbox elements of things, which have got 3 key principles. The first key principle is that of superposition. Now, superposition basically means that it can be anything that is in a quantum state can be a combination. So what we imagine here is if we have a coin, we usually have a discrete coin, which is either a head or a tail. So we've got 2 levels there. And what you can do is you can spin this coin, and as you spin that coin, you don't necessarily know if it's a head or a tail. And we would be describing that as it's in superposition. What you can then do is take a measurement and stop your coin from spinning and look at your result, and you'll find out if you have a head or a tail. This is also something which I'm sure many of you have heard about, which is around Schrodinger's cat. So that in its element is superposition. The next one, which is very important, is entanglement. So this basically means that if you have 2 coins or 2 systems, the result of one depends on the other. So if I spin 2 coins at once, I bring them in, I do some quantum entanglement, which means that they're connected in a very special way. I move them apart. If I spin one in a certain direction, the other is going to spin in the opposite direction, say to have net 0. I can then do a measurement, and if I look at one, I know automatically what the measurement of the other one is going to be, because there is an intrinsic entanglement and dependency between those 2 coins. Now, the final one is uncertainty. So many of you have probably heard of Heisenberg's uncertainty principle, but basically this is the fact that there's a limitation as to how much information one can simultaneously know about a quantum system. So we can know, say, its position and its velocity, but we could only know one of those elements very, very specifically, and the other one remains pretty broad and pretty wide. And that applies to many, many different interlinked variables, such as, for example, time and frequency. So those are the key kind of toolkits and toolbox elements that we have. Now, these toolbox and toolkit elements basically apply at the nanoscale to many, many, many different things. From things that occur naturally in the world, say photonics, atomics, and what we can do is we can start to see the world at the nanoscale, and applying that toolkit that we have, start to control it at that super low energy nanoscale level, which gives us a significant number of platforms that we can start to play with that we call quantum technologies. And these quantum technologies, wrong one, how do I go back? There we go. These quantum technologies can be applied to many, many different applications, to advantages across quantum, say, computing. So we can start to manipulate bits that are now quantum bits to do many, many more powerful things with them. The same with communications. So we can start to exploit those tools for things like quantum key distribution, for secure communications, for encryption. And all of these different applications leverage those fundamental kind of key toolkits that we have. The same is for metrology sensors and timing. There's a quantum world in all of these things that can be used for navigation, for gravity, magnetic field sensors. Suddenly we're incredibly, incredibly sensitive, and we can control them at that level. And of course, atomic clocks as well, for example, at MPL. So the way we can apply all of this kind of underlying quantum mechanics in the real world across a breadth of technologies has a huge plethora of applications. And what we do at OQC is we build quantum computers, and we do that using superconducting circuits, and we have the UK's most advanced quantum computer and the only one that's currently available in the country. And that's just one example of where quantum computing can be applied in the commercial world today. Oh, there we go. Right. The opportunities are wide-reaching, and I know that Peter Knight's going to talk more about this, so I won't go into this in too much detail, but this really does capture some of the opportunities that you can apply quantum mechanics to. Very broad, and this covers, of course, simulation, computation, and everything in between. It's also a global race, so this is an area in which many, sorry, everything keeps skipping. There we go. The whole world is paying attention, and there's a huge amount of funding going into the space. There's also a lot of private funding, private companies playing, for example, IBM, Google, and Tencent, Huawei. Internationally, a lot of companies. I'm sure somebody else will cover more about that as well, but again, just showcasing the importance of quantum technology across the world right now. And it's an entirely new ecosystem, so there is a lot that we need to be considering as well. And again, I'm sure someone will talk further to that. So that was quantum in maybe 10 minutes. And with that, I would like to say thank you very much. And if you've got any further questions, look forward to answering them. Also, you can contact me here.
Alana, thank you very much indeed. Fascinating, and as you said, to try and understand all the depths of quantum technology in 10 minutes is a real challenge, but thank you. You helped us a great deal, I think. I noticed two very quick questions before we then move on to our second speaker, which was one, just on that penultimate slide, one before that even, it showed that the UK was investing 1.3 billion, the USA 1.2, and China 10 billion. Where is that money coming from? I mean, does that really put us second in the world only to China in terms of investing in research in this area? And the second question that's associated with that is, are we interacting, us as individuals, normal citizens, interacting with quantum technology that's being delivered in the real world yet, or is it still theoretical and a research-based technology?
So I'll answer the second question quickly. In terms of are we interacting with this in the daily world? Yes, every day through nature, but in terms of creating it and value, there are examples. So the atomic clocks, for example, that come out of MPL, I'm sure Peter Knight can give you more examples of that, is leveraging quantum technologies and is heavily utilised by the UK's financial markets. Yes, it's not a computer. We don't have quantum computers or new drugs discovered yet using quantum computers on a daily basis in that way. But I think particularly around, say, some of the sensing, communications, timing, this is where there is nearer term applications, and there are live applications that have an impact on individuals, though they probably don't realise it today. To the first question around order of magnitude of funds, just a heads up, those numbers were in dollars. Realistically, we don't know what China's doing, but we do know that there's a lot of money going into it. The UK was pioneering in terms of setting up the National Technology Programme, Quantum Technology Programme, in leading the way, in putting the first phase of that together for the universities. And the world has genuinely looked to the UK in terms of how they set up their international, their programs as well. We have to be able to keep up and compete. Now people have paid attention. Therefore, it's not a time to put our foot on the brake and make sure that we don't have into the usual pitfall of.
Have you froze? Is Alana frozen? Did everyone hear me?
Yes, just seemed to be Alana.
Sorry, Alana, we lost the last bit of your comment there. You seemed to freeze.
Oh no, I have no idea where you lost me. I was giving a very impassioned speech about the UK being top 3.
Thank you. I'm sure that we may come back to that. So thank you very much indeed. Right, we will now go on to our second speaker, which is Roger McKinley. Roger, over to you. 10 minutes, please.
Okay, thank you very much indeed. And Ilana's given a great introduction. One of the things we've learned early in the quantum world is that if you don't cover the science, if you just say what we're doing, people feel incredibly disappointed. So the motto of all of us in quantum is everyone has to get sent home with a balloon and a piece of cake in terms of understanding. And that's been Ilana's job, and she's done it excellently. Let me tell you now the more mundane stuff about what we're doing. If you think quantum's difficult, you try and get government to work together, because that's what we've been doing for the past 6 or 7 years with the UK's National Quantum Technologies Programme. It's a wrapper. It's not a single budget. There is an SRO, Dame Lynn Gladden, the exec chair of EPSRC. But it is a level of coordination which we've managed to maintain. There are some grown-ups there, some real minister-facing departments. We have MOD, GCHQ, and BAYS. And under BAYS, you'll see some of the working parts. So the National Physical Labs is in there, but also, and this started before UKRI was created, you'll see the key research councils in Innovate UK. EPSRC kicked this off when it was fundamentally about investing in universities and research. STFC are more involved now. We've got an ambition for something called the National Quantum Computing Centre, which is the first government lab that we have in the making. And Innovate UK started several years ago, but the big step change in investment in industry came through the industrial strategy at the time and the creation of the Industrial Strategy Challenge Fund. And irrespective of what future there is in that, in terms of future investments, the challenge team have a significant investment to make and monitor through to 31st of March 2025. So we're actually well into a serious program of investment. What does quantum do for us at the moment? Well, the answer is it makes your smartphone work or it doesn't. The world that Ilana described is actually a world which we're increasingly encountering as we've tried to make things smaller. So the chips, which can contain billions of transistors now in a smartphone, are having been designed to avoid quantum effects. But there's a flip side. We want to use quantum effects to do things we've never been able to do before, see things we haven't been able to see before in terms of imaging, sense things which were just, as Ilana described, we've got incredible levels of sensitivity now, sense things we couldn't measure before. There's a property of quantum, which is if you observe a state, you know this property of entanglement, which means it's got a superb application in security. You know if someone's been reading your keys. And computing as well, where there's an opportunity for not just faster computers, but computers which can solve problems we found very, very difficult. These are currently applications where you have to do run after run after run of a program to build up a probabilistic picture, whereas quantum states are very good at maintaining that probabilistic information as you run through a calculation. So there are some intractable problems computing looks at being able to crack. We actually set up 4 quantum hubs. Maybe I'll just go back to those, absolutely matching those areas. It was a competitive tender through EPSRC. We funded universities to carry out the work. And we have Birmingham in sensing, Glasgow imaging, York in comms, and Oxford in computing. They've been running now for several years and into phase 2 of their work. And that, as Ilana said, has been copied around the world, setting up academic hubs. But there are some subtleties. We call it the 1 billion over 10-year program because that's indeed the commitment of funding, and it's well over half through. And that big blue slice is what EPSRC kicked off and is still running with those 4 hubs. And I call that funding universities work with industry. So that's fundamental research. For science, there's still a long way to go, but those hubs were told it had to be with commercialization in mind from the start. And they found about 100 companies, over 100 companies to work with. So when we did the flip side through Innovate UK, which was through wave 2 and wave 3 of the ISCF, we said we're going to fund companies now to work with universities, not universities to work with companies. So we fund big collaborative projects, which I'll come on to, which are industry-led but make use of the universities. And that missing little wedge of 3 slices at the top is what I call facilities and infrastructure. We've already got out of a quantum metrology institute at NPL. We've had some superb demonstrator programs through DSTL, and we have the National Quantum Computing Center, our first national lab relating to quantum, which is beginning to come together now with a management team and plans to get out the ground. So what we've been actually funding in that orange slice is just a heap of projects. Don't try and read this. I will pull metaphorically a few off the top of a pile. But we have about 40 significant projects in flight at the moment, covering all of those areas of quantum. So let me just take you through some of them to give you a flavor of what we're doing. We have an environmental survey company working with 12 different companies there. I just wanted to put up some numbers to show you how many people get involved in these grant-funded collaborative projects, which is a mixture of companies like Teledyne E2V, Unique Lasers. I'll just pull off a few, and research organizations like universities, and the Fraunhofer's in there. And this is to say, can we, to show we can measure gravity sensitively enough to detect things below the surface. Putting up a skyscraper, you always have an unknown before you get out of the ground. Skyscrapers are easy, they live on a small footprint. HS2 is difficult. That is a continuous foundation which will run across areas of mining, Victorian infrastructure, and unknown hazards. And the work here is using a very sensitive gravimeter to be able to detect objects buried under the ground and see underground based on a gravity signature. That program's coming to completion this summer. We have a national gas sensor. So this is imaging, a natural gas sensor run by a company called QLM. Again, 11 people in this significant project, detecting gas leaks, detecting methane. Now, don't think of a handheld detector. Think of a network of cameras that you'd have with number plate recognition, so that around a gas plant or a facility or a pipeline, you will actually be able to automatically detect the release of serious greenhouse gases. Toshiba, that a company that invests heavily in research in the UK, leading another imaging project with LIDAR. This is light radar. So this is building up an image around. Quantum sensors are really transforming this area because of their sensitivity, but other properties relating specifically to these quantum properties. And this would enable an autonomous vehicle or driver assistance to discern what's around it, not just as an ordinary camera, but through obscuration like fog or dust. There are other applications. It's particularly difficult seeing through cloudy water, for example. So seeing through obscuration is important. British Telecom leading a comms project. This is using this property of keys which you know have been intercepted, but not just for transatlantic satellite link, but in a range of what you might call metro communication around a city, including communication, secure communication with autonomous vehicles. And again, 14 people involved in that, including a satellite QKD company called Arkit, which we're forming on another project, which we're funding on another project. And our top universities like Strathclyde, Bristol, Edinburgh involved in these as well. Rigetti is a US quantum computing company with a UK subsidiary. And we have several companies in the UK working on quantum computing. And they're running a project to establish a platform in the UK, working with Oxford Instruments, Standard Chartered, the bank, and Edinburgh University, plus a software company called Phasecraft. So that's another quantum computing applications. And Alana's company, OQC, looking at more about scaling up the creation of the superconducting devices. 6 key companies involved in that, including a company called Kelvin Nano, which is a commercial arm of the nanofabrication facilities in Glasgow. So you'll see these are very different projects. And finally, a software project, River Lane, another UK startup, having built up significant capability in this area, working with others. So here's the trick we do. We provide a grant, but we don't fund a company, we fund a collaborative project. That's the blue square. We add the orange bit, which is the matched funding required from the company. That's private investment. And we spread that out over 3 years on a 3-year project, which is significant. It depends on the size of the company, how much match funding you get. But ambitious companies like Alana's are also wanting to do other things at the same time as run that project. And to do that, they raise private finance. The funding we provide is in a grant. It has to get drawn down. And we're finding that many of the companies we're funding and we've helped get started are now acquiring private finance faster than we provide the grant. And this is why we call this catalytic funding. So to show you where we currently stand, we've allocated, I say carefully, 100 million of grant with 63 million going through some competitions at the moment. That's not left our bank account. That's being drawn down as companies do the work. That's 37 projects. You've seen a few of those, 83 businesses, 30 research organizations involved in those, more being added to the list as we assess for projects we've probably got with that 63 million being allocated. That cohort of companies we already have already raised 100 million of private finance since 2018. So they're raising faster than our grants are being spent. And that's the game here, because quantum computing, yes, it needs, as we talked about, significant public money to help get it started. But eventually, like the Silicon Revolution, it's going to be built on the back of private money. It's a huge market. That figure down at the bottom, which has come from one of the analysts, just gives you an idea of why people are prepared now to pitch private money in as well. Thank you very much.
Roger, thank you. Very interesting. Obviously, it is a very active sector, and there is an awful lot of going on, as you showed in the slide that you suggested we didn't read, but you took us through some of the projects. And I suppose it's a similar question to the one I asked Alana, which is about where we are on the transition from some great ideas, some great collaborations and great science being done to actually seeing the results of that. So when we might see quantum computing more readily used, and we may be already, and it's just we don't know about it. The results of sensing to help build HS2, or is that now happening? So it's sort of on the pathway to full commercialization of the technology. Where do you think we are?
There's a really important aspect to that, which is why we are doing a quantum technologies program in the UK, not just quantum computing, because the technologies are all related. Mastering these quantum effects has dividends across that full spectrum of applications. The trick is that some of those markets are very close. So I think quantum communications is very close. We're already seeing trials and demonstrations. We're seeing companies like BT beginning to put plans in place. Quantum sensing, I know of one company doing a product launch imminently on clever sensing and imaging. And by that, you mean companies who are prepared to announce because they know the phone will ring and someone will want to buy. Quantum computing is really difficult. To some extent, what we're exploiting with the sensing is all the things quantum is sensitive to, gravity, electromagnetism, etc. But to do computing, you've got to shut all of those out so that you can have total control over the states. But this ecosystem we're investing in, the comms sensing very close to market and imaging as well, computing, I think we will see some very interesting machines appearing within the next few years, but it's the real challenge. It's a longer haul and it's going to be expensive. Thank you.
Could you just clarify, with quantum computing, you talked about superconductivity. That presumably has to be done at very, very cold temperatures, or is there a workaround?
There are several technologies, and it's too early to pick a winner. But if you've chosen to do superconducting, you may well have to get down to a temperature which is colder than outer space to get rid of the thermal effects, one of the effects you want to remove. And again, the UK is lucky because one of the leading, if not the leading company in the cryogenic cooling you need for that is Oxford Instruments. So I would say I can enthuse about what we're doing and what we're spending, but the UK has got incredible capability already, which is why it's worthy of this investment. We're building on success and world-class expertise. There are other techniques which don't require the cooling. They have other difficulties, which is why there are several approaches to quantum computing being addressed at the moment.
Fantastic. Thank you. I'm sure there may be some questions around some of that in due course. Right, we'll move on to our third and final presentation, which is from Sir Peter Knight. Sir Peter, if we could have sort of 10 minutes or so from you.
Right. So let's see what we can do in terms of marrying up some of the things that we've just been hearing about science and commercialization. So my role is I chair the advisory board for the UK program. Okay, so let's make a start. We just heard this alluded to in some sense. What we're building on is the use of something called quantum coherence. And I couldn't resist. I'm a physicist. You're going to have an equation. There you go. There's one equation. Quantum coherence is extremely sensitive to the outside world. It's fragile. It becomes exponentially more fragile as the system size grows. So as you get a bigger system, more quantum bits or whatever, the fragility gets worse and worse. So this sensitivity is really our enemy in trying to build a quantum computer with error correction. On the other hand, it's our ally in building a quantum sensor, because this sensitivity is exactly what you need in a sensor. So we control, as Roger says, the influence of the outside world in quantum computing, but we allow it back in when we're building a sensor. And so in my little cartoon from Wojtek Zirek, what you see is this classical world that we're used to, and the quantum world full of these uncertainties and randomness that Ilana mentioned. And the sensitivity to this outside world is what means these coherences really get destroyed in the classical world. That's why we don't see Schrödinger cats in the everyday world. Right, but it's what we need to be able to do to build a quantum machine at scale. So I thought we ought to start by saying, how well are we doing in the UK? So this slide I've got from UVC, which is reviewing the venture capital appetite in Europe. Okay, these numbers are from a while back now. And all of these numbers have expanded greatly in the last few months. So if you look at these, the top cities in terms of startup, by far the biggest is London. If you look at top countries in terms of startups, again, by far the UK. If you look at top cities in accumulated funding, Cambridge comes out at the top of this list. If you look at top countries for cumulative funding, the UK is top of this list. This is for Europe. And remember, all these numbers need to be scaled upwards because of the huge increase in ability to raise capital that Roger mentioned a while ago. Over the past year, we've seen that expansion. Of course, the rest of the world is catching up on this. Now, what are we doing in terms of using this sensitivity? So we're building quantum sensors, we're building timing applications, we're building imaging. So this poor person in the center of this slide looks like it's being tortured. That's actually a brain imaging system. Normally, if you want to monitor brain activity, you use really enormous infrastructure, and it's really very difficult. What we're doing in the National Quantum Program is working at ways in which you use this atomic quantum coherence to map brain electromagnetic activity by building sensors in what looks like a bit like a cycle helmet. That's already being rolled out for practical use in UK hospitals for assisting surgeons who are looking at epilepsy. That's how fast that's moved from a university laboratory in Nottingham to real-world practice with surgeons. We're looking at new time standards, chip-scale atomic clocks, and that is really a major concern of ours to address GPS resilience. We're building a navigation system, chips for accelerometers, gyros, and so on. We can image through walls. We can image around corners using these quantum techniques. As Roger has mentioned, you can use gravity sensors for oil, gas, minerals, and defense applications. The electromagnetic sensors, and that's what the brain imaging helmet is doing. We can use novel cameras with single photon detection. And I'm going to show you something about how that works. Seeing without being seen, seeing the invisible. Okay, so let's have a look at how that sort of thing works. One of the engines in this sort of quantum imaging is the ability to make pairs of light quanta which are twins, entangled. They're absolutely correlated. If you know what one is doing, you know what the other one is doing as well. This is the essence of what Ilana was explaining on entanglement. So we can take blue photons, we can make pairs of photons, twin beams, and we can use them in imaging, in new laser rangefinders. We can use them to see around corners and so on. Of course, they're not very efficient, but we don't want them to be very efficient. Approximately 1 in a billion of these blue photons turn into these pairs, but that's why we're working at the most remarkable sensitivities in this. What can you use it for? Well, Roger's already mentioned the QLM, the quantum startup based in Bristol, using exactly these correlated photons, time correlated photons and single photon counting to look at gas emissions. This is really quite substantial. What you end up with is basically LiDAR imaging down at the single photon level. It's eye safe. It uses telecom technology. It can be rolled up immediately to look at gas leaks and so on, making an enormous impact in understanding what we need to do better in terms of the green economy. Okay, that's the startup from Bristol that Roger mentioned, and there's the detail with their camera that can be used to monitor, for example, emissions from pipelines and from gas handling plants. Let's turn to quantum computing. As I mentioned earlier, it's really difficult to make these quantum bits in these superpositions and protect them. But you don't need that very many of these quantum bits to do something substantial. If I have n of these quantum bits, there are 2 to the n states that I can access. Okay, so if I had 50 quantum bits, really a tiny number compared with the number of bits that you're accessing in a classical laptop, 50 quantum bits under proper control already will outperform a supercomputer, because 2 to the 50 is a huge number. If we can maintain 300 quantum bits under control, and that's the aspiration, there are more states that you can access than there are atoms in the universe. That's the kind of disruptive stuff that we're really talking about in quantum computing. Okay, so where are we? And this is another one I've stolen from UVC. We're in this noisy intermediate quantum era. We're looking at machines that are already demonstrating these kinds of things. And there's a market for these machines in terms of simulations. These are the kind of things that Ilana had mentioned. Within a decade, we'll start to see the broad quantum advantage of this. We'll start to look at error correction. And then in the 20-year timescale, the opportunity to build really full-scale, error-corrected, fault-tolerant machines. And you can see how really rapidly the market builds up for using such a machine. And that's why the race is on worldwide to look at this. In the UK, we have NISQ machines, noisy, intermediate, already capable of doing something interesting, but with a clear roadmap to develop what we want to do next. So we have this chasm. 20 qubits, fair enough, 50 qubits. But then to build a really large machine, error mitigation, there's lots of things we need to better do. And so bridging that chasm is part of our roadmap about what we want to do. And part of the way that we would do that is with the National Quantum Computing Center, which is a major facility as part of the national program. So there's an artist's impression of the building. Construction has actually started. It's on the Harwell campus with the ability to actually start to do engineering scale up and to work with companies in the UK to actually start to deliver an outcome. So procurement from that center has already started. And what we want to be able to do is to establish the National Quantum Computing Center as an assured authority on quantum computing, to focus on the scale up of this, working with companies, supporting the wider ecosystem and so on. Catalyzing the supply chain of what we want to be able to do in terms of the, if you like, the refrigeration units that we were just speaking of for the ultra cold stuff, the laser activity for some of the other platforms, and to be really dynamic and agile in the way that we're supporting the translation of these great ideas into real world applications. So my final slide, a SWOT analysis in terms of opportunities and strengths versus threats. One of the things that we were able to do at a very early stage in the UK, when we started this program more than 6 years ago now, is we built a coherent, unified structure, which is what Roger was telling you about. The National Quantum Technology Program involving all stakeholders, with resource coming from different budgets, but with a common strategic alignment to develop this in terms of sensing, imaging, computation, and communication. We worked really hard to find a way of integrating research and commercialization. And a really important ingredient for this was the importance of the Challenge Fund. In terms of new opportunities that might come up, the new agency, ARIA, is something that we ought to mention. ARIA is meant to be agile, vision-led, and independent. But note, it's only got 200 million per annum compared with 2.5 billion per annum from DARPA. So as a pilot experiment on something that's focused, it's going to be watched with great interest, but remember those resource numbers. Now, how about the threats? Impatience is one of the threats. You know, the ability to say, well, are you delivering things that are generating products now? And as Roger says, in some areas, we are doing that. But in some areas, we need patience. We need patient investment in order to de-risk this large-scale journey, the 20-year journey that I mentioned to fault tolerance. Another threat is lack of continuity, a stop and start as other projects that the nation looks at in terms of science and technology might usurp the place that quantum has occupied. Another threat is hype, of people overselling the product. And we've been extraordinarily careful to explain why this journey is both complex and difficult, but worthwhile. So hype is actually an issue. Another threat that we have to face is the skills shortage. Where do we get people from in this transformational revolution of building a quantum engineering community in the UK? The skills shortage will affect us. There's very rapid expansion in competition internationally, something that Ilana mentioned, where what we see is the UK program, where we really did start of the order of 5 years before other people in a coordinated program. But as part of the COVID recovery plan, we're seeing nations investing in quantum technology at scale. So this year, we've seen announcements from Germany and France for investments of over 2 billion to proceed at scale in quantum technology. So we're in a race, we have been leading it, but unless there is a sense of continuity of support and of expansion and of patience in this one, we're going to lose this race. My final threat that I wanted to mention is premature quantum nationalism, where around the world, the enormous economic opportunities that quantum technology presents has begun to produce a barrier raising effect to inhibit collaboration across the world. And it really is at a premature stage. And certainly we see impacts of that already in the ability of the UK to participate in some of the European Horizon 2020 programs, where we should be collaborating in this one. And premature quantum nationalism is actually affecting us already in that stage. So there's my opportunities, strengths, threats. The UK community is unified, has a sense of mission, is delivering fantastically well. There are products that are already coming out in the market, we can see. There is a roadmap towards the longer term stuff. Young people in particular are finding the field extraordinarily important and interesting and want to take part in it. So it's a race that we intend to maintain our activity in. Thank you.
Peter, thank you. Sir Peter, thank you very much indeed. Very, very interesting indeed. I was interested, you touched, my question was going to be around this skills issue and about inspiring young people to come into the field or to look at the field. Is there an issue about improving understanding within schools so that the potential can be communicated at a younger age to young people so that they potentially understand that this is a whole new emerging field? Or do you not see that as a concern?
No, it is a concern. It's something we're addressing. We're doing a great deal in working on the educational platform in this way. So working with with actually understanding how we can really motivate young people to get involved. And one of the big tricks in this one is not to get old blokes with grey beards to do this, but to get younger people who are really doing it for a living to explain this. And that's what we're doing. And so we've got these great quantum ambassadors that are doing just this. In terms of other parts of the skills, of course, what we need to be able to do in terms of creating quantum engineering is to start working on continuous professional development so that people in other areas of engineering really gear up to understand what the challenges and opportunities are in quantum. So that kind of CPD work, we're working very closely with the IET to develop exactly that process. So skills is a concern. Remember, an awful lot of our skilled workforce in the UK is from other countries. Other countries are expanding their activity and they could hoover up our talent.
We need to make sure our talent pipeline is full. So there is a new challenge. Okay, brilliant.
Full and not leaking.
Not leaking, yes. Yes. But that is an issue for the whole of the engineering sector, isn't it? So we could have a whole meeting on that, I'm sure. But thank you, all three of you, for your very interesting and informative presentations. We've got about, well, I'm not entirely sure because my notes are slightly confused as to what time we are finishing, but roughly around 20 minutes or so, I think, is what was agreed originally. And we have some questions. And the first one is from our president, which is Lord Brewers. Alec, someone will unmute you and please ask your question.
Can you hear me all right?
We can.
Yeah, I was interested to see your numbers, your financial numbers seem to suggest that the investment in the United States is relatively small. Is this really the case?
I think that was Alana's slide, wasn't it? Oh.
So Peter, I think you've been to America and you've seen the program over there. I certainly wouldn't describe it as small, but do you want to talk to that?
Yeah. The National Quantum Initiative, which was signed off by the Trump administration, is taking quite a long time to develop. I was at the White House when we did the launch, in fact. I was one of the 3 aliens allowed in. What they're doing is they're setting up a great deal of activity around really recreating this centers of excellence, the hub idea. So they're kind of slow in that size of investment is actually comparable with what we have. That's what Ilana was showing you. What they have done differently is they provided some resource via NIST, the US version of NPL, to start working on a voice for industry, a thing called the Quantum Economic Development Council, which is funded directly by the National Quantum Initiative to facilitate engagement with industry. That's different to what we're able to do at the moment. So we're looking to people like Ilana as volunteers at this stage. But what we really need to do is to learn from the US program on enhancing that voice for industry.
So IBM has been a real pioneer in this, have they not?
Yes.
Sorry?
IBM has been a real pioneer in this.
Yes.
That's correct. So there's in that slide, there was 1.2 billion, that's the US government, but of course we've also got significant private capital investment going in. So if you start to compare VC, money going into this space, then there is a significant difference, certainly between the US, where typically investors are much more, have a higher risk appetite, significantly deeper pockets, and are ready to kind of follow a space like this and be patient with it compared to the UK. We are seeing that change across UK and Europe slowly. But yes, you know, IBM, Google, these powerhouses that are in America primarily have invested significant money into it. And you've also got very, very large investors that are also, you know, seeing round sizes now of over 200 million regularly going into quantum companies that are startups within America.
Yeah.
Okay, thank you.
Thank you very much. And thanks, Ali. Next question is from Carol Moynihan, who you may be interested in, also chairs the All-Party Parliamentary Group on Photonics.
Thanks very much, Stephen, and great to listen in this evening. And Peter, lovely to see you again, albeit virtually, and hopefully we can grab a glass of something at some point in the next wee while. Oh, well done. I've got a cup of tea sitting beside me. The first thing, Stephen, if you would indulge me just for a moment, just to raise a bit awareness for those members and peers that are in attendance tonight. On Thursday of this week, we actually have our AGM for the Photonics and Quantum APPG, and Stephen's one of our office bearers in that as well. And we'll be looking at, we've got a couple of speakers talking about the opportunities and challenges in funding in this sector. So that should be quite an interesting meeting. So anyone that's available, if you don't have details, I can get these sent to you. So let me know. Really, I mean, I really enjoyed all the presentations, and it's quite good. I still can't get my head around quantum entanglement, and I wish, Peter, you could explain more about these photons, because I'm really struggling with it, even as a physicist, but I think that's part of the nature of quantum, of course. But the question I want to ask, Peter, you're talking about, you know, we've got to get new youngsters into it, and I will declare an interest. My son is just finishing up his master's in advanced research, physics with advanced research, and his final year project was in quantum sensing and looking at single photon detection. So he's doing very well, and he's had a number of job offers, but they're all around the £20,000 a year mark. And as he's saying to me now, he's saying, actually, I'd be better getting a job in Lidl because their management training scheme is a lot more than that. How are we being absolutely serious about getting bright young things into this sector if that's how we're planning to pay them?
Oh, you've read, Carol, absolutely spot on. The bursaries that we pay for our PhD students, who are actually the engines of an awful lot of our program, are really quite pathetic, and they're pathetic compared with our European collaborators as well. So young people with debt already coming out of university are going to find quite a challenge in this one. So the stipends for researchers is a really serious issue.
This isn't actually research positions, this is industry positions. I suppose research positions within industry, and I was just absolutely gobsmacked to find how little they're offering in terms of salary.
Roger, did you want to come in on that? Well,
I think let me set Alana up. I'm quite clear on this. We talked about a 10-year program at least. To maintain our program, I'm looking at the schools. They've got to come through the right education. They've got to be capable of being educated. But having spent 30 years plus in industry, I have absolutely no sympathy with this whatsoever. So Alana, tell them, if you want good people, you got to pay.
If you want good people, you have to pay, and we pay. Certainly, actually, you know, talking to the skills shortage in this space, whether it's different within sensing compared to quantum computing, I'd be really interested to understand, but that figure hugely surprises me. We hire straight out of, you know, either a master's, even out of, you know, without a master's, for example. We pay very competitive local market rates. You know, coming out of a PhD, actually, we have the opposite problem. We have to pay a lot of money for our quantum engineers and our quantum specialist skills right now, particularly where, you know, the US have typical start salaries of $130,000. So I'm pretty surprised buy that. I would advise him to look elsewhere, and I'm sure that there are a number of companies, maybe M Squared, for example, that will pay, fully recognizing the immense skill set that I'm sure your son has.
Thank you.
Thanks very much. And he won't be unique, of course. There'll be a lot of youngsters in similar situation, but thanks very much for that.
Thank you. Thanks, Carol. Right, next question is going to be from Stephen Ben. Stephen.
Hello, thank you very much for your very interesting presentations. Obviously, the power of quantum supercomputing is going to be enormous, but can I ask you about one of the potential threats that hasn't been mentioned so far, which is to modern communications infrastructure? Am I right in thinking that quantum computers could be predicted to factor large numbers very, very quickly and could break the cryptographic codes on which such a great deal currently depends, both in terms of civilian and military communications? And is this an area that is already attracting close interest from, for example, GCHQ and the National Cyber Computing Center? And to what extent is this having an effect on the type of research that is being done?
Okay, let me jump in on that one. Stephen, you're absolutely spot on. What we have to do is to balance the timescales. How long will it take before a large-scale machine is capable of breaking the kind of RSA type encryption that we currently use? And the best estimates that we've got at the moment is such a machine has a likelihood of being built within a decade. Okay, the next thing you need to ask is how long does it take to roll out a quantum resistant secure encryption system that could be used on the internet for trading and so on. So something that's quantum safe. And again, the best estimates on that, and there's a lot of work being done in collaboration with ETSI and ITU and others, is about a decade. So when do you start working on this? You start working on this about 3 years ago. And that's exactly what we're doing. So within the national program, we are funding quite a lot of work on post-quantum algorithms and post-quantum encryption for this already within the civil space and working with companies. Obviously, the National Cybersecurity Center has an active interest in this and work closely with us on this as well. So looking at that space, that's been a core part of our quantum communication hub strategy. And at the same time, we've cross-linked it with our quantum computing and simulation hub to make sure we get the right timescales on this. And we're working on an international scale for this. So there's a thing that NIST is running, which they insist that we do not call a competition, to look at post-quantum algorithms which are quantum safe. That process is well understood, well underway, and is a major international effort. And the UK is playing a leading role.
Thank you.
Thank you, Peter. Right, who are we going to go to next? David Slater and then John Lowe. So David first.
Well, thank you, Stephen. Thanks to all the speakers too. Ilana, a question for Ilana, I think, although maybe the others might have a contribution to make. You talked about entanglement and saying that if you had two entangled quanta that were separated, there would be a unique relationship between the state of one and the state of the other. So if you could measure the state of one, would you know the state of the other without having to wait the speed of light times the distance before you knew the answer?
Great question, David. Ilana.
Yeah, sure. It's a great question. I can absolutely understand how the notion of quantum entanglement and this kind of spooky action at a distance implies the opportunity for instant comms and for breaking the universal laws of physics in breaking the speed of light. I can tell you now, as far as we know, that is not possible. And it is currently impossible. Well, it is impossible to send data using quantum entanglement in that way. What you can do is you can measure correlations separately, and then you can bring that together and compare, for example. So with that, you've still got two kind of data sources, you still then have to bring them together, where you're still going to be limited by however you communicate in that way, through optical fibers, for example. I'm sure Peter Knight can probably give any additional. This is much more your area of expertise than me.
Ilana, you've answered perfectly.
Oh, good, excellent. I had some examples of quantum encryption that were quite fun, because of course we do know that what you can start to do is look at these kind of key distribution, and that was quite interesting, particularly where you can kind of exploit some of these different areas and start to transfer information. So in terms of transferring quantum information in that way, where you can exploit quantum key distribution, which is kind of in the similar area. The most advanced of that is currently in China, and they have a system set up between Beijing and Shanghai. And that's again sent through unbroken optical fibers for around 1,000 kilometers. But that is very different than what you're describing in terms of entanglement, instant understanding.
Thank you. Right. We will move on to our next question, which is from John Lowe, and then I'm going to ask John Dudney.
Thank
so
you.
John Lowe first.
Thank you. I'm here, by the way, from the Institution of Mechanical Engineers, although I'm also a fellow at the IET. This is, I think, mostly a question for Sir Peter, but Roger, you're interested, and I'm glad that Stephen has led the discussion on this already by pointing out the importance of young people. Now, I'd like to, however, encourage you to think even younger than is implied by the questions so far. I think you've got to get your feedstock right. Of course, UKRI held a conference, and I think it was 2019 in Birmingham, which I attended, and it was looking at what UKRI might do at the grassroots level to encourage not just schools, but those who are in the, if you like, the third economy. I happen to help to run an industrial museum, which has a very good track record of education in STEM. We've got a top prize from the IMechE as an illustration of that. And UKRI was looking at saying, well, maybe we can help you. Maybe our grant program can do something about that. In the end, the grant program, we're trying to build an education room, by the way, and the grant program wasn't able to help us. But could you just bring us up to speed about what you're doing, not so much with bursaries and so on, but at the grassroots level, at before youngsters form their career choices? And is there any chance that things like industrial museums with an education program might partner and help you to deliver that?
Thank you, John. Is that one for you, Roger, do you think?
Yeah, let me try and answer it. I mean, first of all, let me put my own cards on the table as an engineer as well, and a fellow in IET. I'm under the cosh to deliver significant societal benefits for the 170 million, if you include Wave 2, which we're putting into some very specific projects at the moment, and prove it has societal impact and economic impact. And I'm doing that through collaborative R&D, and I'm desperately using the product of our education system to do that. But you're absolutely right. There is a UKR interest which goes back before that, and it's not just UKRI. I think when Peter mentioned the ARIA program, I think it was interesting that we've got to remember that the most successful countries we're competing with and successfully competing with have many items in the toolbox. And if you're suggesting, which I can believe, that there is still some tools missing in terms of how we get that engagement at an even earlier age, then I will take that message back home quite definitely. But we're very reliant on the Institute of Physics, for example, the engineering institutions and other professional organizations to help with this. But I can certainly get you more information if you reach back further down the age group. It's not where my feet are being held to the fire at the moment.
Okay, you will find my address on the Q&A. So if you want to drop me a line, Roger, that would be very helpful.
I will do. Yep.
Yeah, John, if I could jump in as well on this one. There's a number of experiments underway using museums around the country to provide hands-on experience and some demonstrators. In Scotland, I know Miles Paget is working quite closely with the museums in Scotland on these kinds of things. Perhaps what we need to be able to do is to actually pull some of these threads together and share best practice to work out what can be done. So I think let's follow that up offline, because I think there are some things underway, including the Science Museum in London.
Well, we are linked to the Science Museum. I'd be delighted to help you. Just again, look at Q&A, email addresses there, or PNSE can trace me. Thanks, Peter.
Right. Good.
John,
Yeah.
now we'll go on to John Dudley, and then that will be followed by Isabel Pollock.
Thank you, Stephen. First of all, I'd like to say that the three talks have been extremely good, and I was particularly struck by Jana's outstanding exposition on quantum weirdness for the simple-minded. Really excellent.
Thank you.
But my question, I suppose, is really to Ilana. You talked about having the only quantum computer in the United Kingdom. I'd be interested to know whether there is any practical program running on that computer at present that outperforms conventional computing, and to what extent does it do it?
Thank you. Before, I'm just going to correct one thing. There are quite a number of quantum computers in the UK around different research institutes and companies. We have the only commercially available one, which means that if you want to come and as an end user run an application, then we can host that through our private cloud access today. So first of all, just clarifying that there. Secondly, so in terms of practical applications, the type of customers and end users that are typically most interested and do, run algorithms regularly on commercially available quantum computers, typically do so to understand the technology and to understand where it's going to disrupt them as a business. And there are algorithms that are still very small scale, but right now these algorithms can still all be simulated by a supercomputer. So you can start to do different things around, say, molecular dynamics is quite often like very small algorithms like that. Looking around as well, random number generation. These are different types of applications that run today, but ultimately don't run on, you could run them on a supercomputer if you have enough time and enough cores. Now, the experiment, which is the very infamous one within the last few years, was run by Google, and that was called, unfortunately, they named it quantum supremacy, and I like to call that quantum advantage. But this was really the first experiment that was really pushing that boundary of what you cannot simulate on a classical supercomputer. It's since been done, but that was a benchmark point, and that was really the turning point for that. And this means that any system that's going to start outperforming and is truly providing that quantum advantage, we ultimately need three things. We need bigger quantum systems, so more quantum bits. They all need to be very high quality, which means ultimately have high coherence and low error rates. And we also need to be able to control and manipulate them effectively. And that those three fundamental areas right now, the race is on to achieve all of those three things in parallel so that we can start moving from where we are today, which primarily are these toy demonstrators ultimately, into this what's called NISQ era that was talked about earlier, where you can start to simulate systems primarily for, say, quantum chemistry applications on a 3 to 5 year type of time scale, that we should start seeing more impactful, commercially useful things happening. So does that answer your question?
Yes, thank you. I think that does. Thank you.
Thank you, John. Just to confirm, are our speakers happy to continue for a few more minutes?
Yeah.
I think we've only got a couple more questions. So the next one is from Isabel Pollock. Isabel, hi.
Hello. Thank you. 3 great speeches. And I recognize that you are making significant progress and achieving a lot. I was prompted by one of the quotations on Ilana's presentation from Carl Williams at NIST, sort of suggesting we are limited perhaps by our imagination. So I just wondered, what would the team suggest we might need more of to make even more progress, or are we happy with the progress we're making? So is it vision, is it imagination, is it funding, is it skills, or is it something else?
Who would like to try that one?
I'm happy to go first on that.
Thank you, Roger.
I think the question we had on education was an interesting one. We've talked a lot about money, and money really does matter. This expression, punching above your weight, is an excuse. If we want the benefits of quantum, we're going to have to need to continue to invest. However, when it comes to real impact, including some great careers, I'm sure it's the people who you encounter on the way who make the big difference. So there's many a young person who wants to become a physicist or engineer, having met the right person. And I really think, what we really want more of is this magic factor X, which is the great mind, of which we've got some very good ones in the UK, with the right inquisitiveness and a commercial bent. And actually, I would say that is what we're being envied for at the moment, because we are creating an ecosystem and we're throwing up not only clever scientists, but whereas, if you like, in the good old-fashioned dot-com era, it was people with MBAs who wanted to find a way to make a buck. But now we're actually finding people with quantum PhDs who want to find a way of making a buck. And when the UK looks back on a success, it will be from this magic combination of science and the desire to make a difference, including through business, which has been driving that. I really think we've got culturally an incredibly strong position here. We just need more of it.
Brilliant. Thank you, Roger. I don't know if anyone wanted to add anything to that. If not,
I had a few thoughts if there's time.
Okay, thank you, Ilana.
So I was going to say my team certainly don't lack vision. I think that's the first point. I think the visionary scientists we have here and the entrepreneurial mindset of the UK academics that have spun out all of these companies is something that continues to impress me. For me, market pull is one of the key things. So making sure that the key stakeholders within these companies that this technology is going to be revolutionary for are engaged and are engaging early enough. For me, I very much feel that once customers and market pull is present, then the ecosystem will develop a lot more on its own, which is of course where a lot of the focus of the national programme is on identifying those customers and making sure that they're quantum ready and engaged. So I think having that focus there, making sure that the market is aware and engaged is something I would like to see more of. And then finally, whilst my team have vision, unfortunately, we are all too British still in Britain. And I think as a culture, and particularly potentially within the VC world, making sure that we have the visionary investors that are going to be able to see this through is going to be incredibly important for the success of the quantum space in the UK.
Thank you. Okay, I think we've got 2 or 3 more questions. So if we keep them short and snappy, we should get through them in good time. So the next one is from Ed Hill, and then I think Carol Moynihan wants a quick follow-up, and then I'll go to Neil Gasper and we'll finish off with Julian Potter. So Ed.
Fine, thank you, Stephen. Can you hear me okay?
Yes.
Great. So I'd like to know, how significant do you think the national security considerations are in driving what was referred to previously as quantum nationalism as distinct from economic advantage? To what degree is there an analogy with the nuclear arms race? That, of course, was funded very strongly with public investment in a very sort of secure way, whereas this sounds like a much more of an open innovation approach. But to what extent are these massive security implications likely to be a driver in some of the nationalism, and indeed some care needed in terms of the degree of sharing of IP and such like?
Right. Can I deal with that one? For the most part, it's economic considerations that are the driver. People can see that this is a disruptive technology that can be transformational. They want to position their nation to get the best return on their taxpayer investment. The security side of it is being used as a kind of vehicle for raising those barriers. And for the most part, at this stage, in this early stage technology, it's spurious. But on the other hand, it's being used to justify barriers that are being erected. The main driver on this is to try to secure the economic advantage for the particular region that's funding the activity. That's the main driver. But to some extent, they're hiding behind security implications to justify those barriers. And if you like, they're working on a script which is quite analogous to what was used for the exclusion of the UK in Galileo, for example. Entirely spurious, in other words. There are security implications for quantum technology. They're well understood, and there are ways and means in which one can deal with those aspects. But a lot of the quantum nationalism is being fueled by economic advantage for those nations.
Yeah, thank you very much.
Thank you. I think that's right. That's very clear. And I think Carol's question, are you still with us, Carol? Sort of follows on a little bit from that, doesn't it?
Yes, thanks, Stephen. It totally follows on from that, because I mean, I've met with sort of sector representatives who talk about the difficulty for small companies in particular in trying to attract funding. And if the only funding that is being is coming their way, sorry, is from countries like China, they're having to take it. But of course, there's big implications in terms of security, in terms of the IP as well. So I just wonder, are we taking it seriously enough when we're looking at scale-up funding, for example, for small businesses in this area?
Well, yeah, okay, let me jump in again. We need to do a great deal more, Carol, in that space. There is some activity funded via the British Business Bank, which is actually proving to be really, really helpful for the startup communities to survive the fairly difficult phase that they're in at the beginning of this. But it needs to be enhanced very dramatically. We actually need a co-investment strategy to enable a scale up so that companies like Ilana's will prosper in the UK. There is a tidal wave of other investor money that's around. Not all of it will be welcome. On the other hand, we're in a very long journey for this, and one needs to be able to be patient. So patient capital is important. The enhancement of the British Business Bank and NSIF is going to be really important for exactly this.
Peter, do you want to talk to the bill?
No.
Okay.
Could I just add one thing? I mean, quantum shows all the signs of being a sticky technology. Where the skills are, where the intellectual engine room is in terms of universities, where the right sort of entrepreneurs are is difficult to create. We've got it in the UK. I just love investment from anywhere, as long as it's going to feed jobs which have to stay in the UK. Opportunities like this are rare, and quantum is showing all the attributes of one of these sticky technologies, which is things we dream of, and we're being handed one at the moment.
Fantastic. That's quite a positive assessment. So thanks for that, Roger. Right. Now we'll go to Neil Gaspar, and then, as I said, the final question will be from Julian Potter. So, Neil.
Good evening. Good evening. Wave someone if you can hear me.
Yes, I can hear you.
Yeah, excellent. Right, thank you, speaker. So Neil Gaspar from the Atomic Weapons Establishment. My question is probably more for Roger, but for anyone can answer really. We've heard a lot about quantum computers and the fullness of their benefits being a little way off, and NISC era. Ilana talked about some benefits sort of nearer term. But with quantum computing, there's hardware and software, and we're learning a lot from quantum algorithms, even on classical computing. So my question is, are we capturing those benefits to the UK in terms of sort of return on investment and you know, the core benefits that you're after for the UK? Are we capturing quantum algorithms on classical as a benefit?
Yes, yes. I mean, I know exactly what you mean, and the gesture says it all. The more we've looked at quantum computing and understanding what quantum software is, the more we realize how much we can do with relatively small machines. And at the same time, people like Alana are bringing forward in time the prospect of having larger machines. So we got a pincer movement where quantum is looking useful much earlier than we would have thought a few years ago. That's obviously not an atomic clock, I think. I've lost count now. But yeah, it's coming forward. It's coming forward in time significantly. The best place of catching this is in smart companies like Riverlane's a good example. Alana's doing work with Riverlane as well. All of our new companies are very, very good at collaborating, and we're going to get big benefits from them wrapping that knowledge up in all sorts of instruments. One of the most exciting ones Riverlane is doing is actually an operating system. Which means that where the cleverness lies in algorithms isn't going to be restricted to what machines it can get used on.
Right. But look, people are already testing some of the early algorithms on classical emulators. So up at the Harshey Center in Daresbury, they have purchased an emulator, and a number of large companies in the UK are testing some of their algorithmic work on exactly that emulator at Daresbury. At the same time, in Oxford, Simon Benjamin and others have built one of the world's fastest quantum emulators. These are classical machines for which you can test drive, if you like, novel architectures and novel simulations. We are really doing rather well in this space.
Brilliant. Thank you. And as I said, final question, which I think again follows on quite neatly from that, is from Julian Potter. Julian.
Thank you. Good evening, and thank you for 3 excellent presentations. One of the best examples of entanglement, which I still don't get, I've ever had. Keep working at it, Alana. My question, does quantum computing merely mean faster processing, or is there a shift in what the computer can do? And this comes from my interest in AI, where the more stuff you can process, the quicker people think it's thinking. But what can a computer do that's running on a quantum system? Is there such a thing as quantum cognition? Will there be such a thing as quantum cognition?
Thank you, Julian. Interesting question to finish up. Who would like to go first? I think if I could have a comment from each of you on this and then sort of just wrap up what you've heard this evening, that would be really useful. So, Ilana?
Yeah, quantum computers are not simply smaller, better, faster, regular computers. Because they operate off quantum principles, it means that you can do things and simulate the quantum world as we know it in ways which are just fundamentally not possible with classical computers or supercomputers, and that's what makes them so incredibly powerful. So this is where quantum simulation, molecular dynamics, materials discovery, all of these different types of applications are for me most exciting, because we're opening up a world of things that would just literally not possible, because you cannot simulate quantum with classical. You cannot do it accurately or effectively, which is why you need that quantum computer for that. And that covers the quantum simulation side or the quantum laboratory, where it can be more of a tool, but as Peter said, spoke to, opens up exponentially more states and more power, is more of the data processing side. So that is, I would say, more analogous, whatever the word is, to a tool similar to applying AI, for example. But even then, the order of magnitude of change of what you could do, can you imagine a world where you can solve multivariable problems, 5 or 6 variables, and find optimal solutions in very short time periods? That's, again, completely game-changing.
Thank you. Roger, do you want to?
Yes, certainly. I mean, we had a chat with the financial community actually recently on this. So sit up and take notice if you're someone who uses a computer expecting a different answer each time, because these are the users we're really after. These are people who are trying to crack really difficult problems where they're having to change parameter and run simulation after simulation after simulation. These are people trying to optimize something. It could be the traveling sales algorithm. It could be Netflix with a huge data set trying to guess what movie to offer you next, which you're guaranteed to take. Okay, so this world of optimization is very closely linked to competitive and financial advantage. And that is where quantum computers, with their ability to hang on to this probabilistic information and not, as in classical computers, just require a century or so of turning a handle, show enormous advantage.
Thank you. And almost final word to Peter.
We're right at the very beginning of this journey. What we know is that quantum computing is transformative. And we're beginning to get to grips with opportunities, as Ilana and Roger have just explained. The analogy actually is with the position we were in when Bell Labs started to invest in semiconductors to build the first transistor. Okay? And they persuaded the board to build the world's first transistor because they had a single application in mind, the hearing aid, a compact amplifier. What we're in the middle of doing is we've got quantum hearing aids. They're the beginnings of it, but imagination will take off in just the same way that when transistors were available, the whole world changed. And it's imagination that really is going to take us to places that at the moment we haven't even thought of. We've got quantum hearing aids, but we're going to do so much more.
Well, fantastic. I think that's a really encouraging and uplifting point which to finish. I think we all understand the huge potential and the even if we don't understand the technology, however well it's tried to be explained to us for the heart of thinking, it's particularly around entanglement. I've got to find a way of explaining or understanding that. But anyway, I was glad that one of the physicists first said they didn't understand entanglement before I made myself look foolish. But it has been an absolutely fantastic discussion, really interesting, and to the point at which I can't wait for the next 5, 10, 20 years to pass so we can see where this technology does lead, because there are many things that we would not have predicted 20 or so years ago based upon technology that was around then, that have transformed our lives. So yeah, I think it's a watch this space with great excitement. And thank you for sharing that excitement with us this evening. And it's certainly come across your enthusiasm and well, knowledge, commitment to the area. So that really brings us to the end of our discussion this evening. Can I thank my 3 panelists, Ilana, Roger and Sir Peter, for their contributions. It's been fantastic. Can I also thank David Kunar from Innovate UK, who helped facilitate this discussion. Thank you, David. And of course, I want to thank our audience and our questioners for their contribution. And of course, I need to thank the Parliamentary and Scientific Committee team, which is Karen Smith, John Slater, Ben Allen, and Alfie Hoare, who will be writing up today's reports for our quarterly magazine, Science in Parliament, which, just to reiterate, now goes to every member of both the Commons and the Lords. So thank you for that. And of course, thank you to our Chief Executive, Lee Jeffs, for his ongoing support for the committee and keeping us on the straight and narrow. So thank you all. I don't think I've missed anyone out. Our next meeting will be on the morning of Monday, the 17th of May at 10:30, and that is being organised in partnership with the Physiological Society, and the title for that discussion is "What is the role of science in delivering the government's plan to build back better?" Interesting subject. We've obviously been through quite a challenging time, but I think as we emerge, and today is the day, you know, we take another step towards a new sense of normality, building back better is going to be vitally important, and science and technology and engineering and maths will have a huge role to play in that and in shaping our future from here on in.